Hello, good morning one and all. I'm Vishal. I'm here to explain about high gain observers in feedback control application to permanent magnet synchronous motor. So I'm here in third year of triple engineering triple department. So here here we are going into high gain observers in feedback control application to permanent magnet synchronous motors. So high gain observers play an important role in the design of feedback control for nonlinear systems. This article overviews the essentials of this technique, starting with motivating that illustrate the main features of high gain observers, with emphasis on the peaking phenomenon and the So, high gain observers play an important role in the design of feedback control of nonlinear systems. This article overviews the essentials of this technique, starting with motivating that illustrate the main feature of high gain observers, with emphasis on the peaking phenomenon and the role of control saturation in dealing with it. The observer design for single output and multi-output systems is presented along with the use of the observer in feedback control. A nonlinear separation principle is discussed, and the use of an extended high gain observer as a disturbance estimator is covered. The most serious challenge is implementing high gain observers is the effect of measurement noise, which is covered next. The article ends by presenting an experimental application of the extended high gain high gain observer to speed control of a permanent magnet synchronous motor PMSM. So here we can see the under the stated assumptions there is such that for 0 is less than gamma is less than gamma. The estimation errors xi is equal to xi minus xi cap. For 1 is less than or equal to I less than or equal to p for the high gain observer rho. So here in the 21st equation we can see xi is less than or equal to maximum of b x bar of x bar of 0 by e power of minus 1. So for some positive constants a comma b comma c, the two terms on the right hand side of 21 show bounds on the estimation error due to two sources. The term b by e power of minus e by 0 x by 0 power of omega t by e is due to the initial estimation error. X bar of 0 is equals to x of 0 minus x bar of 0. It exhibits the peaking phenomenon and illustrates that the estimation error decays rapidly to small values. In particular, given any positive constant Ka, it can be seen that b by e power of p minus 3 e power of minus 80 by e using IH opticals rule. It can be seen that limitations e to 0, e tends to 0, t of e is equal to 0. The second term e power of p plus 1 minus ICM is due to the error is in modeling the function phi. This error does not exist if the observer is implemented with phi is equal to phi naught. The high gain observer design can be extended so classes of multi-output systems and reference there in the simple case omega is equals to f naught of omega x comma u, xi is equals to xi plus u. Input the last integrator in each chain the function iz, which could depend on all integrator states as well as the state w and the input u without loss of generality. It is assumed that each chain has at least two integrators, that is, two at a chain of a single integrator can be included in the equation. f of 0 is equals to 0. The model 23 to 26 arises naturally in mechanical and electromechanical systems where displacement variables are measured but their derivatives, that is velocities and accelerations, are not. For example, the nonlinear dynamics of an M-link robot take from the form m of q bar plus c of q comma q bar plus q bar into q bar plus dq bar plus g of q is equals to ui, where q is an m-directional vector of generalized coordinates representing joint positions, m-dimensional control torque input, and m of q a symmetric positive definite inertia matrix. The terms c of q comma q bar dq and G of P account for centrifugal, Coriolis forces, viscous damping, and the gravity respectively. If the measured variables are the joint positions, takes the form with xi q is equals to qi, x2 is equals to qi, pi is equals to 2. The multivariable normal form of nonlinear system having a well-defined vector relative degree is a special case of relative nonlinear systems where omega is a sufficiently small positive constant and the positive constants alpha I. Feedback control. Consider the multi-input, multi-output nonlinear system. Omega is equals to f naught of omega x comma u. X is equals to x plus b phi of omega x comma u. C is equals to y is equals to cx. So here we can see with the matrix AI is equals to it's a linear B transposition C100, where P1 GT of T is equals to plus represent P chains of integrators, and equations are the same but written is in a more compact form, where dr omega 1 dr x1 are domains that contains their respective origins. Moreover, stabilizes a two-step approach is used to design the output feedback control. First, a partial state feedback controller that uses the measurement of x is designed to asymptotically stabilize the origin. Then a high gain observer is used to estimate x from y, and the state feedback controller is allowed to be a dynamical system of the form. The extended high gain observer for the two-dimensional systems of the second order observer estimates x1 and its derivative. If an estimate of the second derivative equal to PO was available, it would have provided an estimate of the function, which could play an important role in control design. In particular, if Z is a disturbance term, the observer acts as a disturbance estimator. Disturbance estimators are widely used in feedback control. See for a comprehensive coverage of the topic, and see also for the use of disturbance estimators in active disturbance rejection control. An observer that estimates the function Z is called extend high gain observer. It is illustrated in the next example. So here we can see the system example. X1 is equals to x2 of phi of x2 t comma x plus u, y is equals to x1. So here the matrix x is equals to 0 1 minus 1 minus 1, x1 is equals to x2, x2 is equals to gamma plus u, sigma plus u, sigma is equals to sigma gamma phi of t comma x comma u, y is equals to x1. Considered under the assumptions the closed loop system, suppose that d is constant, it continuously differentiable, has a unique solution for each d double is an exponential stable equilibrium point, then there exists such that converges to 0. Here the graph we can see which in the time, and it is a simulation graph phi of t comma x. We can see it is increasing, it is slowly decreasing in the first graph. In the second graph it is slowly increasing from low to high and from high to high. dt belongs to non-compact where while meeting certain requirements on the transient response, the design is pursued for minimum phase systems for which assumption 3 is satisfied. There exists a radially unbounded positive definite function. Thank you so much.